Episode 12 of the World of FPGA podcast. To design an SoC is quite different from designing only a single device like a microcontroller, a processor, or an FPGA. The high-level workflow is topic of this episode. Welcome to the World of FPGA podcast. I'm your host, David Kirchner, and I will lead you through the world of FPGA. And now, let's begin. Developing an SoC has more parts than other developments. For example, like you're developing an application, or today it's called only app, or you are creating a controller program for microcontroller, or something like that. SoCs contain multiple different systems. That's because it's a system on a chip. And in these podcast series, actually, we're talking about SoCs which combining an FPGA with, for example, an ARM core. So we have at least an FPGA development and an ARM development. Maybe also the configuration and generation of an operation system. Since I'm very firm in Xilinx components and the development system from Xilinx, we will now dive into the workflow of Xilinx Vivado. But in my opinion, other systems will work quite similar. So how would this workflow look like? Starting your computer, grab a cup of coffee, log in and start Vivado. Alright, let's put joking aside. Starting from we have all open. We create a new project and also a new block design. This is not a must-have, but it's quite easier to have this block design and throwing all the blocks from Xilinx into this design. For example, we're putting our processing system into it. We have our microblades, and we have also, or we can also use other soft IP core processors we can put into our design. But if you have a sync the SoC from Xilinx, combining an FPGA and two ARM cores, then it's you will normally want to use the ARM core, and for this you put your processing system IP block into your design. After that, you're connecting the logic things and the interfaces and create maybe your system you want to have later on. And never forget constraints for pinout and timing. And after you have created your logic design, I call it logic design because in the sync it's the PL, it is a programmable logic part. The other side is the PS, the processing side. So you have the PS and PL. And after creating your logic, you can now synthesize this and you can run through the implementation of your design. After that, you can generate the bit stream and if everything is correct, you will have at the end a bit file for your logic design. And now you have to export the design, which also includes the bit stream. And now we are done. We have our FPGA design done. That's the one part of the SoC design. And now we have to switch to our software development system. In the Xilinx world, this could be for until the version 2018 or 2019. It was the SDK. And today it is Vitis. But the workflow for both systems is nearly the same, so I will go through also in a top level manner, not too deep into the tools. So we have to import first our created and exported hardware. This is, I haven't mentioned it, this is a file. Xilinx has the file extension XSA. and it is a zip file. If you changing the ending to zip, you can just open it with your program of your choice. And in this zip file is included the bit stream. There is included all the code you need to initialize your processing system. You have some system information also about your block design and so on. So there are a lot of information the software development system needs to create your program. So after you have imported your hardware, you can now create your platform and your software project. There are two different things here. We have on the one hand the platform on which our software is running, and we have our software project we want to create. Most time you will need a first stage bootloader. In short, it's called FSBL, and this FSBL is used from the FPGA to load the bit stream into the FPGA and also to load the application into the RAM. And today we will only create a bare metal application. A bare metal application is a running program without an operating system, so like we have most time in microcontroller applications or things like that. So, and if you have only a single program you want to run, which is going step by step through its source, through its code, then a bare metal application could be the choice, the right choice for you. Another area where bare metal applications could be very interesting are real-time applications. Yes, I know there are real-time operating systems which running with specific timing informations, but on the other hand, if you have a more or less simple application where you are communicate with the other systems and then doing something, then communicate, then doing something, that's also good to implement in a bare metal application running on an ARM core. Well, this is possible to run two different applications because, for example, in a Zynq you have two independent ARM cores. Other SoCs have maybe much more cores and they can run more applications. And it could be an idea to have one core for your communication stuff and one core for your real-time control of your system. Well, and after compiling your platform together with the FSBL and your applications you want to put, you can now combine everything into one block. So you have a combination of your application binaries and your FPGA bitstream in one file, and this one file you can, for example, program into your flash memory on your FPGA, on your SoC board, or you can put it on an SD card if your system can boot from it, and then run your system. Well, that's all for today. Just give you an idea, an introduction into this, into development of an SoC. In the next episode, we will talk about embedded systems, and there we can use a lot of our learnings from today. I hope you have much fun, and if you're searching for more information, just go to the show notes and you will find them together with my newsletter on world-fpga.com/WFP012. If you found this episode helpful, please rate it on Apple Podcasts and share it with your colleagues and friends. That's the end of today's podcast episode. Thank you for listening and for your attention. So I say goodbye here next time, your David Kirchner.